Okay, now we're going to look at the Pythagorean Theorem. We're going to do a proof of the Pythagorean Theorem to show that all the time, if you take a right triangle, and this angle right here is 90 degrees, then if you take the length of this side, so length, the one-dimensional length, and then you square it, so you take that length times the same length, we call that a squared. And you compared and you added also this length times itself, so b squared. If you added the number of squares here and the number of squares here, it always happens to be that it will add up to the number of squares that you would get by multiplying this length times this length. So just a numerical example would be if we had a 3 by 3, and this is 4 by 4. So there's 9 plus 16, you would have 25 over here. So this is a special triangle that we call the 3, 4, 5 right triangle. 9 plus 16 is 25, and 5 times 5 is also 25. So this is a special triangle that we're going to be talking about with the Pythagorean theorem. So written out explicitly, it's a squared plus b squared equals c squared. And there are a number of proofs. If you go to this website, you can see 98 different proofs that show that this is always true. I'm just going to do one of them here. So we want to make it general so that any square, so this is a square that's a by a, and I'll make another square over here that's b by b. Now if I threw this distance right here, b, over here, if I cut it off of this square, I made that distance b, and I drew my right triangle in there. So I called this b, and this is a, and then I'll call this c as the distance, the one-dimensional length from that corner to that corner would be called c. And if I drew another triangle right here from that same point up to that corner, this would also be b. Now this length right here, how long is that? Well, it's actually also a. So let me just redraw this line here. This is a and this is b, right? If I took off b from this end, right? So on the top, I'm gonna have this is a and this is b. So if this was like 5 and this was 3, the length would be 8. Now if I took off 3 from this side, so I'd have 8 minus 3, I'd still have 5, right? And you can play around with the numbers and figure out that this always happens to be a right here, this length right here. So this length right here is a. So yeah, 8 minus 3 is 5 if I were to use numbers. Now, so if this is a and this is b, and we have a right angle here, and this is a square, so this is a right angle here. So if you play around with that L shape, this L shape gets rotated over to that L shape, and you can use your isometry to see that a rotation and a translation, this always happens to be the same triangle. This would have to then be also C. So we have C and C. Now what I want to do is I want to take this triangle right here and cut it off, and I want to take this triangle right here and cut it off, and I'm going to move them. Okay, so I'm going to take this triangle and I'm going to actually rotate it about this point. So if you use your isometry and you rotate this triangle over to here so that this right angle ends up right there, and this length right here would be a, right? So I'm taking a and it goes up there, and this is b, and we know that because our square was b by b, so that matches up. And then this length right here is C, right? And then I'm going to take this triangle and rotate it up here to sit into this right angle. Okay, so this is length B and this is length A, and if I rotate up there, this is length A just because it's part of the square and my rotation, so it's an isometry, it's a congruent triangle. And now my new triangle over there also has a hypotenuse. The distance, the longest distance of the triangle is called the hypotenuse, is also C. So I have this new shape, these are now gone, and I have this shape which happens to be a square that is C by C. So the area of that square would be C times C, or C squared. So what did I start with? I started with a square that was B squared and A squared. So the total number of squares, the area of this square, say it was 5 by 5, it would be 25. And say this was 3 by 3, that would be 9. So I had 25 plus 9. Now I'd have to have that many squares over here, so 34. So A squared plus B squared would have to equal C squared. And just with my numbers, I said, well, what if it was 25 plus 9? This would have to be 34. Now, can you take any two numbers and multiply them together to get 34? Right, so if C squared is 34, what is C? That's the question, right? Well, you can try a few numbers. You can try, well, 6 times 6, right, equals 36. Well, that's too high, so let's go down. 5 times 5, well, that gives me 25. So it's something between 5 and 6, right? So you can try things like 5.5 times 5.5. And you can keep trying things until you get a number, or you can just plug it into your calculator and see what you get. It's called the square root. So C squared, you take the square root of both sides, and you get C is equal to the square root of 34. And let's see if I can pull that up on my calculator here. Square root of 34. So my guess was right, 5.830. So approximately equals 5.831. And we use like little squiggly equals to say approximately equals. Okay, so that's a numerical representation of the general proof that I just did.